In this video, I'll show you how to solve the ALEKS problem called deciding the relative energy of electron subshells. This problem is really easy to solve if you know how to use the periodic table to come up with electron configurations. But if you don't know how to do that, don't worry, I'm going to give you some tips that'll make this problem really easy. So you can see here that I've got a periodic table that is color-coded at 4 different areas. Before I talk about that color coding, I want to point 2 things out. First of all, this element is highlighted. I want you to ignore the highlighting on that element. I took a screenshot of this periodic table from a different ALEKS problem that was asking me a question about this particular element, which is why it's highlighted. But for this problem, I just want you to pretend like that is just green. You probably also noticed that I highlighted in this area where there is no element, and I did not highlight helium. And that is because when we're doing electron configuration type stuff, it is more logical for us to think about helium as if it is located at the top of column 2A, right next to hydrogen. And it doesn't make a ton of sense for us to think about helium in its normal location, which is at the top of column 8A. So we're just going to pretend like it is not over here. So as I said, we've got these 4 different areas of the periodic table color-coded. Each of those 4 areas pertains to the different types of orbitals: the s orbital, the p orbital, the d orbital, and the f orbital. This first couple of columns of the pink area of the periodic table, this corresponds to the s orbitals. And as you know, there isn't just a single s orbital. They have principal quantum numbers associated with them: 1s, 2s, 3s, 3s, 4s, etc. That principal quantum number comes from the group number, or the number of the horizontal row on the periodic table. So this area of the periodic table, which is in row number 1 and in the columns associated with the s orbitals, these are the 1s. This is the 1s area, and this is the 2s area, and this is the 3s area, etc. You get the idea. I'm going to number those more later. This part of the periodic table, this part corresponds to the p orbitals. The stuff that is in green corresponds to the d orbitals, and then the stuff down here in this purple color, they correspond to the f orbitals. Now, before we get too much further, I think it's really helpful for us to think about the periodic table in its full expanded form. So you may or may not already know this, but this version of the periodic table is actually the true periodic table cut up so that it fits well on a piece of paper. The actual periodic table is actually expanded out, so I can just kind of take these and just sort of move them out of the way. And this part of the periodic table actually belongs right here. And so we just take our representation of the periodic table and we chop it up to make it fit on a piece of paper better, but this is what it actually looks like that. And I am just going to rewrite this F up on top so it's consistent. Okay, so going back to the principal quantum numbers, as you know, as I explained, these numbers pertain to the energy level, or the principal quantum number, the numbers that come before the letters with the orbitals. And for the s orbitals, everything just matches up perfectly. So this area, which is associated with 1 and s, this is the 1s area. This would be the 2s. This is 3s. This is 4s. This is 5s. And you get the idea. Next, in energy, you know, we have the p orbitals. They're all the way over here on the other side. So we've got to be kind of careful when we're looking across. If we look in the 1 column or row, there aren't any p orbitals at all in the 1 area, and that's because we know that the 1p is not an actual thing. It doesn't actually exist. So the p orbitals, they actually start on the 2nd row. This area right here, this is corresponding to the 2nd row on the periodic table, and the p area. So all of these are the 2p orbitals, and then under them we have the 3p and the 4p and the 5p and the 6p. Now for the d orbitals, these guys right here, they are actually lagging behind in terms of numbers. So these d orbitals, which are actually in the 4th row on the periodic table, they're in row number 4. These guys are actually the 3d orbitals. So all of the d orbitals are behind one number in terms of that group number. So these are all going to be our d orbitals, one number behind the corresponding p and the corresponding s orbitals. And then last but not least, we have the f orbitals, and the f orbitals are one number behind the d orbitals. So this area, this f orbital, one number behind its corresponding d orbital. So that would make this 4f, and the one underneath it would be 5f. Now, to read the relative energy of these orbitals, we start at hydrogen, and then we just move from left to right and from top to bottom, just staying in each row across the periodic table. And this gives us the relative energy of the orbitals. The orbitals are in order of increasing energy in this way. So the lowest is 1s, and then 2s, and then 2p, 3s, and then 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d. You get the idea. So I have in my problem, I'm going to use a different color here. I have a 3d. Oh, no, I don't have a 3d. I have 3p. I have 2p. I have 3s, and I have 4s. And looking at my periodic table, starting here at the top and just reading across, I can see that I'm going to come to 2p first. So that is my lowest energy. And then after 2p, I'm going to come to 3s. And then after 3s, I'm going to come to 3p. And then after that is 4s.